Okay. I think we can start. I'm Anthony Boisserie from Ampere, Renault Group, and I am your Master of Ceremony for the first session of the afternoon. So welcome to this session. During this session, we have two presentations. The first one is entitled 10BASE-T1S In-Vehicle Network Validation. And we have two speakers. Thomas Schamberger works at TDK. He leads application development, including analysis, simulation, and testing. And he contributes actively to the development of industry standards within committees such as Open Alliance and ASA Motion Link. And Patrick Isensee started his career at CNSS, focusing on the physical layer of automotive communication protocols. Currently, Patrick leads CNS Consulting Department, where he evaluates and promotes emerging multi-drop technologies through theoretical analysis, simulation, and testing. Thomas, Patrick, the stage is yours.
Okay, thank you. Yeah, thanks a lot for the kind introduction. It's a great honor to be here today at this part of this event. And yeah, hello everyone. So my name is Patrick Isensee. I'm from CNS Group in Germany. And with me is Thomas Schamberger from TDK Electronics. And together we will guide you through today's presentation regarding the physical layer validation and testing of 10BASE-T1S networks, focusing on extended designs and power over data line. So as some of you might already know, I had the joy to become a father last year. And Thomas, on the other hand, is navigating fatherhood for quite some time. So we are both very familiar with storytelling. And don't get me wrong, so our aim today is not to lull you into sleep. So, I mean, it worked well when I practiced this presentation with my little daughter. She fell asleep at slide number 2, I guess, which is probably the main reason why she's not with us today. I think a 1.5-year-old has other interests. But I hope that your interests are in line with ours, especially considering that you're very familiar already with 10BASE-T1S. So let's have a closer look on today's agenda and dive into the world of 10BASE-T1S. Okay. At first, I will shortly go and talk about some validation criteria which are currently available for 10BASE-T1S systems. Here, the focus is really the signal integrity analysis. We'll also talk about simulation because this is a very easy part to do the validation. And I will also show and share some first results of the simulation from, or the impact of a power over data line in a network. And after that, I will take over to Thomas, and he will give you way more details about the components that are used in power over data line. Okay. So as I said before, let's turn this into a story. So imagine yourself as a little child with sparkling eyes, hearing about new activities or advances in the 10BASE-T1S universe. So once upon a time, highly valued colleague at BMW, Kirsten Matthäus, had the goal to establish a new technical committee at Open Alliance to really cover or find gaps in the standard, cover them with new specifications, but also develop test specifications for compliance testing, IOPT, and also EMC. So I'm talking about TC14, and this was 7 years ago. So trust me, I've double-checked this number. And today, we're not talking about anymore about a multi-drop system with its PLCA, if it's possible or not. With Ethernet. 7 years later, we talk about final silicons. We talk about established interoperability. We talk about PMD transceivers and power over data line to really lower the costs at the end. We talk about topology discovery and also MACsec. So when you or take part in yesterday's open all-member meeting, you have already heard that TC14 have closed or almost all specification, almost all work is done right now. So there are only small steps left that we need to consider. And when you are fine with all these definitions and parameters given in these specifications, then you're done. So there's no need, from my perspective, that you run further investigations like simulations and measurements to check the signal integrity at the end. But this presentation is a little bit more for the people that thinking outside the box. Yeah? If you have some requirements that are not fulfilled by the standard and the specifications. So that means maybe you have use cases or interest to see if something like a stub is possible in 10BASE-T1S. So you don't need, or don't want to stuck with these 10 centimeter stubs, or what I call the daisy chain at the end. Maybe you have some other requirements regarding the channel. Maybe you don't want to use a perfect 100 ohm impedance cable. Maybe you have something else in mind. Same situation for power data line. So we will see later on if this have an impact on the signal integrity and if further investigations are needed or not. Okay. So I'm talking now a bit about the validation criteria. For all of these are or can be used also in measurements or some of these things. But for me, simulation is a very, very good tool to cover really these investigations, these further investigations for 10BASE-T1S and also for other technologies. So I think if you're familiar with simulations, then all these advantages here on this slide are very clear. And you will never ask this question that is shown here, why is in-vehicle network simulation so important? Why is even at all simulation is so important? So for sure, we have a total cost reduction, a short development time, because it's way faster to run a simulation compared to a measurement. But I wanted to a little bit go or spend more words on the two remaining topics that are shown here. First of all, we have a quality assurance, which means that I have a precise knowledge of every transmitter-receiver combination in the network. So it's not only one point that I measure and validate or judge the whole network. So I really know every point in the network. And which is way more important is the broader analysis. So with this, I mean corner cases, real corner cases, like where things like temperature ranges are included, or production spread. So this is something you cannot run with a measurement at all. And at the end, you have to question yourself, does one measurement of a prototype represent the whole production? And from our aspect, it's not covering it at all. So there are many things that can be affect here at this point. So with all that said, simulation is the most important phase during the validation process of today's complex topologies. The only thing which is not so nice talking about simulation is or you have to care about talking about simulation, are the simulation models for sure and the tooling. So when both are fine, you have done everything, then there are only advantages at the end. So what we are doing in our simulation is that we use only some models, so not all that is in the real measurement given. So we have models for the phi, we have common mode choke models, transmission line models, and all passive components at the end, like resistors, capacitors, and so on. We, for example, don't use any microcontroller model just to lower the complexity of the simulation and also the simulation time we need at the end. This means that also no interface like MII, SPI, and so on is included. Here we really concentrate on the signal integrity. and the signal shape on the bus. Yeah, what we see here is what we are doing during the model development that we are doing for these components. We really make a single device check or some measurements that we are sure that the simulation model reflects the curve shape of real devices. So this is the important thing here. We do this for a single device, but also we do this for a full network. So after the single device verification, we do the network verification to check the behavior of the driver, the different input-output filter, threshold voltages, bus levels, and so on. And what I can say at this point is we at CNS have really the experience of 15 years of simulation for different technologies, for sure. But we never saw a surprising result that was not visible in the simulation. And this is the important thing here. So you really can rely on the results given in the simulation. So now let's talk about the validation criteria. So I'm not sure if you're all familiar with these Open Alliance specifications. For example, this one here, we have the system implementation specification, where this mask is included and defined. So we have this well-known plus minus 30 millivolt for a minimum time of at least 25 nanoseconds. And for first implementations, because 10BASE-T1S is not on the field right now, so it's really the first implementation that will come up during the next time. So we have the feeling that we really need some safety here. So there are several things you can consider. You can just make your network smaller, for example. There's also a way just to gain experience on the field and so on. But we can also include something like a second mask, a warning mask, to establish a little bit more robustness into the network and the validation, to have a better feeling, increase the experiences on the field during the first cars on the market. And after that, maybe the warning mask can be done smaller, or you can just get rid of it at all. Yes. So the warning mask itself can be done with just a random percentage that can be defined. So this may be the worst way to do it, just to say, okay, it's 10% bigger than the fail mask. I really recommend to make another approach here, just to include your experience you already have in your measurements, for example. Or what we are currently doing is make an initial simulation run and include in this run some noise injection with, for example, 200 millivolt peak-to-peak Gaussian noise. And this is also defined in the system implementation. You can increase this number, you can decrease this number. And this difference here can be included into the warning mask, and then you're done. Yes. And maybe one important point I wanted to mention here is that, I'm a CAN person, so I came from CAN, CAN-FD, CAN-XL. And when I see a mask like this in a CAN world, I would say this will never work. So I had some doubts when I started the investigations here and starting the simulation and also measurements that we have done. And I was really surprised how robust the current implementations and PHYs are on the market. So it's really, we make really measurements where we increase the noise injection to a point where the whole signal is very, very noisy. And we just scratched a little bit of the mask, but everything was fine. So it was working. It was really, really robust at the end. So we can also trust on the definitions given in open at this point. Okay, what we have also in our investigations are some informative criteria. All of this information is already given in the eye diagram that you have saw earlier. So in an eye diagram, you see the eye width, the eye height, you see the jitter effect. All of these are included. But at the end, we make out all of this. We make a heat map for these three parameters, just to see how the parameters is changing. Because if you wanted to check an effect and you started to compare some eyes, it could be challenging. That's why we included some heat map like given here in the slide, just to see and compare the real findings, the real values, and also to see where's the worst case value given in this particular network. Okay, now I come spend some words regarding the first simulation results we have done for power over data line. So our goal was to see the impact of this power over data line on the signal integrity at the end. To do this, we have chosen two different topology designs. One of them you will be familiar with. I will show you later on. And one of them is quite specific and special. So beside the two networks, we have also done different supply voltages like 12, 25, and 48 voltage. We have included some corner cases, like I said before, temperature effect, and also the production spread into the phi and the transmission line model. And what is also not included in this specification, unfortunately, because of the submission deadline of the presentation, is the impact of this Gaussian noise injection. So, but if you have questions here, want to see some results, just contact me later on. That's no problem. Some things are not included here. We are working on this, so we'll make an update here in the future. I think the first topic is not that important. We have not included the charging transients in the ramp-up phase. So this is something that is existing also in reality, so that all these components are fully loaded. But we just waited a couple of microseconds to have this effect done, and then we are running our simulations. The topic which is quite more important, I think, is the impact of the voltage regulators in the PSE and PD. So power sourcing equipment, which gives the power, and also the powered devices, which receives the power. Here we could have some switching noise that we could see in the signal integrity, but this is not included here. Okay, I see the time here. I need to speed up a little bit. So this is just the circuitry of the ECUs. We have done some changes regarding some investigations that Microchip has already done in the past regarding the end node termination. You see here on the left. The drop node is as specified in the system implementation specification. Here you see the first topology. So this is the one that is defined or used in TC14 in the interoperability test specification, also in the tests. So you should be quite familiar with this. We have the termination not on the ECUs. We have this into the harness. And we just choose ECU1 for the PSE. So it's just an example topology to show you the impact here. For sure, all the other ECUs could also be the PSE. So this is how this signal looks like. We have the blue line here is the reference signal without a power data line. And the red one is really the impact of the power of the data line. And you see that the impact increases, talking about higher power supply voltages at the end. Yes. as I said, I need to speed up a little bit. This is the second one, the much more crazy network here we have. So this is completely out of range of the rules given in the standard. We have real stubs 1 meter and above, but we have less total cable lengths, which also limits a little bit the impact of the power data line on the signal. One point I like to really point out here, and which is very important just to avoid any misunderstanding here, is that this is not the worst case signal you see here on the slide. This is just the signal which have the highest impact of power over data line. There are other ECU transmitter-receiver combinations which are way worse than this, where we have really reflections due to the stubs and so on. Okay, and at this point, I'd like to hand over to Thomas, who will give you some more information about, or more details about the components that are used in power over data line.
Yeah, hello to everybody. I'm Thomas from TDK. So I will go into detail about the passive components used in 10BASE-T1S, and then especially for the power, so the power over data line. So as we know, we can see here the PoE, the power over Ethernet, the TX, with the center tap trafo here. And here we can see the single pair Ethernet power, also named power pool, so power over data line, or sometimes SPoE or MPoE. So I want to point out here, so there are different ways to implement it. So to filtering the COM mode choke noise, you need a COM mode choke, which can be seen here. But to filter the differential mode noise from the power side, you need a differential mode inductor. And then you can place the differential mode inductor behind the COM mode choke or in front of the COM mode choke. And there is a mistake. So this would be line side injection, not phi side injection. And this is phi side injection. So the line side injection will help us that the current flows through the DMI and not through the COM mode choke. And so you can downsize the COM mode choke because it doesn't see the high current. Okay. And then this is, if you cross out the DMI here, this is from the Open Alliance system implementation spec. So you have the phi here, the COM mode choke as close as possible to the phi, and then the blocking caps, and a COM mode or differential and termination. And you would place here the DMI and some ESD components. And then it's possible to implement this with 2 single inductors or with 1 differential mode inductor. Yes, the next step. So there is possibilities to implement it with 2 single inductors or 1 DMI. So there are advantages and disadvantages of this. So with the DMI implementation, you will get a way better mode conversion because of the symmetry of the part. Because with 2 single inductors, you need to have a really low tolerance between each other. And you can also downsize the component. Okay, and what is the right impedance for the differential mode inductor or the single inductors? So there we can have a look in the IEEE specification from the CG, where you can also take into account the voltage group, and then that the 10BASE-T1S is a Manchester coding, so it has 1 volt. And if you do your calculations, then you end up for a differential mode inductor with inductance of around about 36 microhenry for 1 leg. And in total, I call this here L poodle. This would be around about 110 microhenry to guarantee the impedance which is needed for the bus. And for a single inductors, this should be around about 67 microhenry. Okay, and then if you have a look in the Open Alliance in the TC14 implementation specification of the 10BASE-TS, they refer there that the capacitance, maximum capacitance, which should be for the node is 25 picofarads. So you will also have there the 10 picofarads from the COM mode choke and from the tracing and so on. And at the end of the day, this means you need to bring also the stray capacitance, so the unwanted capacitance of the DMI to a low level, which should stay under 5 picofarad to guarantee the 25 picofarad overall. And then I want to point out here, so as we know, there are power classes defined in the 802.3 BU and in the CG, which you can see here, but there are no power classes defined for 10BASE-T1S pool implementation. Yeah. So there are different ways to implement this pool. So you can implement the COM mode termination before the capacitors or behind the capacitors, depending. Okay, then I have to hurry up. So I have some measurements here. To crystal this down, to simplify everything, you will just see here the COM mode choke and the DMI and nothing else. And on this slide, you can see basically a comparison between two single inductors with different tolerances. For example, here, this shows you 15% tolerance between two single inductors, and this line would be the DMI, and you can see when the tolerance is higher, you cross the limits because you are not so symmetric on the mode conversion. Okay, and here I have a measurement of a COM mode choke and a DMI. So I always ground one side of the DMI, and then I measure from this side to this side with a VNA. And here you can see the mode conversion. Okay, and the next important parameter is the return loss. So this is the STD11, also measured from the COM mode choke and the DMI. You can see the different measurements here used by different COM mode chokes and differential mode inductors. Okay, and then I summarized the measurements from the different components which were used. So here are the COM mode choke, and here are the different DMIs which are used with a low stray capacitance below 5 picofarad to guarantee a good eye diagram. Yeah. So this is a kind of a conclusion of the different DMIs for different voltages and different current sets. So then we can come to the conclusion.
Yeah, to summarize all of it that has been said, is that we can say that complex topologies and advanced features like power over data line will always result in further improved processes, since they will have an impact on the signal integrity. So simulation at the end is always a good and efficient way to do this check and to see these effects on this signal on a very early stage of the in-vehicle network development. And the next steps that we see at CNS side at least is that maybe some continuous standardization work is needed. For example, like Thomas mentioned, we don't have any specifications done for power over data line for multi-drop systems like 10BASE-T1S. So this could be something. Also, the model development is also something that we derived from FlexRay and also from CanWorld to now automotive Ethernet, but maybe there's something need to be included, especially for 10BASE-T1S. This could be also discussed in a small group. And after that, we will we currently receive some hardware to do some verification measurements on the result we show today on the simulation. And we are also very interested in doing some simulation stuff for the node compensation, like it was presented by ADI on the last Ethernet Congress. So this we will also include here in the simulations. And at this point, I'd like to thank a lot for your attention, and we're open to answer your questions here. Thank you.
Thank you, Thomas. Thank you, Patrick, for your presentation. Sorry, but we have no time for questions. So
okay.
Please go after the next one during the break in the corner speaker. Thank you.